We learned in class about waves and all the different parts of a wave, the amplitude, the wavelength, the frequency. In this mini lecture, we're going to learn the calculations that we can make on waves. We can quantify information about waves. One thing to keep in mind is that all waves on the electromagnetic spectrum are light, and therefore they travel at the speed of light when they're in a vacuum. There is a relationship between the frequency and wavelength of light. The relationship looks like this. C equals lambda nu. C is the speed of light. The speed of light has been found to be 3.00 times 10 to the 8th meters per second. And as you can recall from our lecture earlier, lambda is the wavelength of a wave, and nu, this is lambda by the way, lambda, and nu is the frequency of a wave. So what scientists have figured out is that when you take the product of the wavelength and the frequency for a given wave, you always get the speed of light. Now we're going to take a look at an example in calculating with our relationship between frequency and wavelength and the speed of light. In this example, we are asked to calculate the frequency of a wave that has a wavelength of 3.2 nanometers. One thing you have to keep in mind is that we have to always be in meters for our wavelength. And in this particular problem, we're given nanometers. So we're going to have to use dimensional analysis to first convert the nanometers to meters. When we use dimensional analysis, recall we always write our given value first, along with the unit, nanometers. We want to get rid of nanometers, and if you recall, we get 1 billion, or 1 times 10 to the 9th, nanometers for every 1 meter. When we calculate this, we get 3.2 times 10 to the negative 9th meters. Now we have a wavelength in a unit that we can use. We can now plug that in to our speed of light equation. C equals lambda nu. We're asked for frequency, so we want to get nu. Let's rearrange the equation before we plug and chug. So in order to do that, we divide by lambda on both sides. So frequency, nu, is equal to the speed of light divided by the wavelength, or lambda. Now we can just plug and chug. C is the speed of light, 3.00 times 10 to the 8th meters per second. And we're going to divide that by 3.2 times 10 to the negative 9th meters. Our meters cancel out and we're left with 1 over second, which is hertz. When we run our calculation on our calculator, you should get 9.4. We can only keep 2 sig figs because of the 3.2. Times 10 to the 16th hertz, or 1 over seconds. This is frequency. Please pause the tape here. Make sure you can get the exact same answers I got using your calculator. It's very important that you know how to enter numbers and values in scientific notation properly in your calculator. In 1900, a guy by the name of Max Planck was able to identify a way for us to calculate the energy of a wave. We knew at the time that different types of light have different amounts of energy. And Planck said that there is a limit on the amount of energy that an object emits or absorbs. He called that amount a quantum. Quantum simply means a fixed amount. with his work, Planck was able to establish an equation for energy. In this equation, we don't use Q. The reason why we don't use Q for energy is because we're borrowing it from physics. E is energy, and it is equal to h nu. Now, E stands for energy, and again, because we're borrowing this from physics, we don't use the letter Q. H is what we call Planck's constant, and its value, right here, is 6.6262 times 10 to the negative 34th joules times seconds. And once again, nu, the Greek letter nu, is what we know as frequency. So there's a direct relationship between the frequency of a wave and its energy. Let's take a look at this example. Ramon's favorite radio station is 92.3 FM. What is the wavelength of this station, and what is the energy of this station? One thing to keep in mind from our talk earlier in the day about electromagnetic spectrum, FM, whenever we're talking about radio stations, FM is really 92.3 megahertz. So the radio station value is the frequency of that particular radio wave. The problem is that we can't be in megahertz. We have to convert this to hertz. So let's first take care of that. So 92.3 megahertz. Remember, mega means a million. So 1 megahertz is equal to 1 million, or 1 times 10 to the 6th hertz. When you run this calculation, you should get 9.23 times 10 to the 7th hertz. Now we can use our speed of light equation, where we multiply wavelength and frequency, in order to calculate the wavelength. So let's take a look at how we do that. C equals lambda nu. This time we want lambda, so we're going to divide by nu. So lambda is equal to the speed of light, 3.00 times 10 to the 8th meters per second, divided by our frequency, 9.23 times 10 to the 7th hertz, which is actually, hold on one second. Remember, hertz is 1 over seconds, so we can rewrite hertz as 1 over seconds. Why would we want to do that? Because then we can cancel out seconds and we're left with meters. Our final answer here is that lambda is equal to 3.25 meters. This takes care of the first question. The second question asks us what the energy is of the radio wave for this station. So that requires us to use the other equation, E equals h nu. This is a simple plug and chug equation for us. H is again Planck's constant, 6.6262 times 10 to the negative 34th, make that a 3, joules times seconds. And we're going to multiply that by the frequency, 9.23 times 10 to the 7th 1 over second cycles for hertz. The reason again is we want to be able to cancel out our seconds. So we write 1 over seconds instead of hertz. When you run this calculation on your calculator, you should get 6.12, we need 3 significant figures, times 10 to the negative 26 joules. This is an extremely small amount of energy, 6.12 times 10 to the negative 22nd joules. Our last slide for today has us looking at something called the photoelectric effect. The problem that scientists were having was electrons. Electrons are particles, and they're matter. They have mass and they have volume. But scientists were looking at this because they were starting to think that perhaps electrons did not necessarily act as particles all the time. And in doing this, they took a look at physics. And in 1905, Einstein concluded that a light wave could also act as a particle. And when it did that, he called that light wave particle a photon. And the reason why he came up with this is because of something called the photoelectric effect that scientists could not explain. See, at certain energies of light, scientists noticed that they could eject an electron from a piece of metal when they shone the light on the piece of metal. But not every light was able to do this. For instance, if you take a look here, red light was too weak to knock any electrons out. But green light and anything with a higher frequency than green light is capable of knocking electrons off of the metal. No one understood why. So it was Einstein that came along and said that light consists of quanta of energy that behave like particles. So once a wave hits a certain amount of energy, it acts as a particle and can literally knock electrons off of atoms. It wasn't until 1923, however, when Arthur Compton was able to confirm this idea of Einstein's with real research evidence. We will continue this talk and see why we care about light and waves and particles and what it has to do with electrons tomorrow.